Hello. Welcome to the Topology Design lesson. In this lesson, we will explore key concepts related to designing the layout of Apogee components across your physical or virtual infrastructure. Let's jump into details. A clear understanding of the responsibilities of each Apogee component is required to successfully design your topology. We covered Apogee component responsibilities in detail as part of the Technology Stack lesson. If you haven't completed that lesson, please pause this video and complete it prior to continuing with topology design. Apogee Edge components can be arranged into multiple groupings we call topologies. These topologies range from a single machine to many machines in different data centers. The Apogee Edge architecture is horizontally scalable. This is true for all components. On the diagram, nodes correspond to physical or virtual servers. Each node contains one or more Apogee components. Each component represents one or more processes hosted on those nodes. Depending on the requirements, nodes are added to the topology design to meet capacity, availability, resiliency, and network zoning requirements. A typical Apogee Edge topology looks like this. By typical, I mean the placement of components across nodes, not necessarily the number of nodes. Let's explore the diagram from left to right. Node 1 shows three components: UI, Management Server, and OpenLDAP. This is a common configuration option. These components are all associated with management functions, and it makes sense for them to be together on the same node. In this two-region topology, we illustrate high availability for management functions. This is represented on node 11. Each planet only needs one management server, but having two or more is possible. The need for more than one management server will be driven by requirements such as availability and resiliency for the management capability. Nodes 2, 3, 4, 12, 13, and 14 host Cassandra and Zookeeper components. Both Cassandra and Zookeeper are clustered technologies. On this diagram, we illustrate a Cassandra ring composed of 6 nodes and a Zookeeper ensemble with the same number of nodes. Any Apogee Edge topology beyond a single node, all-in-one installation, requires 3 Cassandra servers per region. This requirement is driven by the Cassandra replication factor and query read-write consistency configured in Apogee Edge. Since Zookeeper and Cassandra share nodes, we recommend having the same number of Cassandra and Zookeeper processes on each node. Making all data store nodes containing Cassandra and Zookeeper equal makes capacity planning, monitoring, and automation easier. In order to guarantee a consistent view of configuration data across the cluster, Zookeeper uses a voting mechanism. We recommend having an odd number of Zookeeper voters in the cluster. If you have an even number of Zookeeper nodes, make one an observer. On the diagram, voters and observers are highlighted by the subscript found next to ZK. For example, ZKV represents a voter, while ZKO represents an observer. The Zookeeper voting mechanism is described in more detail in the official Zookeeper documentation. Nodes 5, 6, 7, 15, 16, and 17 correspond to the gateway. These nodes contain routers and message processors. A typical Apogee topology places both routers and message processors on the same server. It is possible for you to host routers and message processors on different machines. Separation of these processes is only needed if network zone requirements call for it. The number of routers and message processors is driven by requirements and capacity planning. The minimum requirement is one of each, but most production installations will have 2 or more per region. Routers and message processors are stateless and horizontally scalable. They can be added and removed quickly if necessary. Nodes 8, 9, 18, and 19 host Cupid and Cupid server components. A typical topology has 2 Cupid nodes per region. Adding more Cupids is possible, but rarely needed for most installations. Nodes 10 and 20 are the Postgres nodes. These nodes host PostgreSQL, as well as the analytics aggregation process called Postgres Server. On the diagram, we indicate that the PostgreSQL master is located in region 1. The PostgreSQL standby is in region 2. This is indicated by the subscript shown next to each PG. Depending on your analytics capacity and network requirements, Cupid and Postgres components may be combined on the same server. This is typically the case for non-production planets. In production, most customers have Cupid servers separate from Postgres servers. The green horizontal lines going across regions correspond to eventually consistent data replication. Please notice that the developer portal is not included on the diagram. An additional node to host developer portal and its PostgreSQL database may be required. The Apigee Edge installation guide, located at docs.apigee.com, describes multiple sample installation topologies and patterns you can use as a starting point when designing your topology. Apigee Edge is built to scale. The architecture and technologies selected allow you to scale horizontally. Horizontal scalability applies not only to components in the same region, but also across regions. Apigee Edge planets can contain 1, 2, 3, or more regions. As you scale horizontally and add regions to a planet, remember that not all components need to scale equally. Adding components for a specific functional area must be driven by requirements associated with that area. For example, on the diagram, we illustrate 3 regions. Regions 1 and 2 possess the same number of components. In both regions, we find UIs, management servers, OpenLDAP, and Postgres servers. Region N looks different. In this region, only specific components are present. The minimum set of components required in a region contains Cassandra, Zookeeper, Cupid, and 1 or more routers and message processors. Having a clear understanding of components' roles and responsibilities, as well as the architecture characteristics of Edge, makes it easy to identify problems, plan for capacity needs, and monitor the platform. It is important to remember that, most of the time, components can horizontally scale across the functional groups shown here, independently of each other. Depending on API traffic patterns and availability needs, you may need to add additional capacity to components in a different functional group as you grow the number of components in one group. For example, you can add routers and message processors without having to worry about management or developer components. If the number of message processors increases due to more API calls, at some point in time you may need to add capacity to PostgreSQL or revisit your analytics data retention period. We will discuss capacity planning in more detail later on. For now, remember the grouping of components. By design, Apigee Edge is active-active. Depending on your needs, you can decide to send API traffic to 1 or more regions. It is possible to route API traffic using active-passive regions, active-active regions, or geolocation. Typically, global load balancing or DNS resolution will be used. Let's use the diagram to illustrate runtime API traffic data flow. An API call initiated by a client application will be directed by the global load balancer to a specific region. All traffic arriving in the region typically passes through a local load balancer before hitting an Apigee router. Once API calls arrive at the router, they will remain in the same region. Apigee routers and message processors are configured to direct calls to only local resources within the same gateway pod. API calls that arrive at the router are directed to one of the available message processors. Message processors execute API calls. Depending on the API proxy implementation, APIs may call Cassandra to store or retrieve data, as well as call 1 or more backend systems. API proxies may call backend systems in the same region or across regions. The decision is based on the API proxy implementation and target server configuration. Analytics data flow works as follows. Analytics events are generated by the message processors. Message processors asynchronously send these events to Cupid. Cupid servers read data from Cupid queues and write data to PostgreSQL. Notice that all Cupid servers connect to the PostgreSQL master, as only that database is writable. Standby databases are read-only. Over time, the PostgreSQL master replicates data to all standby databases. Analytics events generated by the message processors contain raw data about each API request. This raw data is aggregated by the Postgres server. Apigee Edge allows you to query both raw and aggregated data. Most reports visualized in the UI are powered by aggregated data. Custom reports provided by Edge use raw data. As you design your topology, it is important to consider your organization and environment design. Organizations and environments can be added at any time. You can also allocate underlying resources to different organizations or environments at any time. We covered this topic in detail as part of the Terminology and Organizational Structure lesson. On Apigee Edge, it is possible to control environment scope. Message processors are associated with environments. This association controls whether a given message processor will process API calls for a particular environment. Typically, all message processors are associated with each environment. On the diagram, we illustrate the association between environment A and all available message processors. As new environments are added, they can share the existing physical capacity on the system. In the second example, we show that environment A and B are associated with all available message processors. This is a common design option. Most customers share message processors across one or more environments. If required, it is possible to allocate dedicated processing capacity to specific environments. In the third example, we illustrate dedicated processing capacity being allocated to environment A and B. You can associate and disassociate message processors with environments at any time using the Management API. The association between message processors and environments can be useful in scenarios where physical separation of internal and external API traffic is required due to network zoning requirements. If required, routers and message processors can be placed in different network zones. Environments can be used to separate API deployments and traffic. For more information on this topic, refer to our documentation. If you have any questions, please post them on our community. Thanks for watching.